All right, so since we are in Switzerland, we start exactly on time. My name is Gilles Dubocher. I'm the head of open science here at EPFL in the Vice-President's Academy. It's really a great pleasure to welcome you here for a presentation that is important for me for both two reasons. One, because I think what we're going to hear about today, the story of Scala and the Scala community, is something that is hugely important in the way I like to think about open science. Open science too often is seen as an administrative burden, something that you see through GLPs or requirements, but that's not what open science is. Open science is actually something that happens in labs, in science, in research communities that has a real life to it. And we want to showcase that. We want to show what it means to do open science with these showcase events, of which this is the first one, I think we can say. I'm also very pleased that this is our first showcase because I have, as you will probably hear, a personal connection to Scala. I was at some point involved in this, I think, amazing project. So it's really a great pleasure to hear about it again 15 years after that. It's also, I think, in a way where I learned what open science feels like in the flesh, and that still today gives a lot of the, I would say, impetus for why I want to be involved in that. And why I want to carry forward. So first I'd like to introduce Noémie Mazaret, who is working in the open science team and who is really the brain and the arms behind the setup of this series. I let you present the series and also the speakers, and thank you very much for doing all the work for organizing that.
Sure. Okay, so welcome everyone. Thank you for being so many here for our first episode of the Open Science Showcase series. So as Gilles described a little bit, this series is really to introduce successful, inspiring projects that are going on here on campus, and for once in a while, not focusing only on the science behind the project, but also on the logic, on the rationale behind the mind of its creator as to why they wanted to make it an open project and what it entails for a researcher's career. So actually, this first episode is a perfect example of that, because we will introduce the story of Scala, introduced by Martin Odeski, who is the great mind behind this whole very successful project of Scala, who really had the vision to take it forward and build a community that now gathers over 1 million users. So he will tell us a little bit more about the story of it all. And then Darja, who made the courageous leap from political sciences in 2017 to join the Scala Center and is now the executive director of this team of computer scientists, will explain to us a little bit more about what it entails to run a nonprofit center in computer science and how to build a community and how to push open science forward. So on this, Martin, I leave you the floor.
Good. So, thank you for the invitation. It's a pleasure to inaugurate this series here on open science showcases. And in the case of Scala, it's really an open science and an open source showcase. So open source is at least as important. I have been at EPFL since 1999, and I had the LAMP, which is the Laboratoire des Méthodes de Programmation. So, our research is mostly about programming languages. So why do we have research on programming languages? Well, the fundamental problem we need to tackle is complexity of software. We all know software is very complex, and there are multiple reasons for it, why it has to be complex. One is it models a complex world. The world is complex. The things we model are complex. And the second thing is, unlike bridges, software changes extremely rapidly. A bridge, people ask, well, why do bridges not fall over all the time? Well, they're designed for 10 years and they last 100 years, whereas in software, what you design today might have to be redesigned 6 months from now or something like that. So the time scale is much faster. So over the last decades, the research community has gradually developed two tools that help tame complexity. One is functional programming, and the other is strong types. And that was sort of the origin of Scala, which combines functional programming with object programming, which at the time was the industry standard. So Scala has this motto, which says we want to use functions for the logic and objects as modules or objects as components. And it was the first mainstream language to fully support FP with strong types. So the history is the project started in 2001, shortly after I arrived at EPFL. And I should say that I had this project or something like that in mind for a long time, but it was only at EPFL that I had the long-term funding that actually let me do that. Because as we're going to see, things like that are very, very unpopular in the early stages with grant agencies and things like that. It's very, very hard to get grants for large, long visions like that. So it was this sort of unlimited, no, limited, but unlimited in time check from EPFL that says, well, you have this funding and you have it for as long as you are here, and that actually helped start the project. So our first experimental release was in 2004. We used it in the first course internally. In 2003, I think Gilles was a student in this course. It was quite all right. I remembered I sort of, there was a hiccup with the compiler. So the compiler was not ready at the beginning, of course. So I set to essentially write myself big parts of the compiler. And I did that in essentially in all-nighters and things like that. And I can remember, boy, was I relieved when the Easter break came along, because that allowed me to essentially get 1 week of head start for the next module. So it was crazy. But anyway, so that was then. And then there were basically, we had, I think, maybe 2 or 3 outside users at the time. Most programming languages have that. And then for some miraculous thing, adoption started in 2009, 2010. That was mostly due to some people in San Francisco that the first one was the Lift framework. There was something that was a popular framework in Ruby on Rails, and they thought they could do this with a strongly typed language, and Scala, it had to be flexible because the Ruby language was flexible, so Scala was such a language, and they used it for that. But it was still sort of very, very experimental. And then essentially Twitter found out about it. But by then, Twitter at the time was a company with 25 employees total, so it was a startup. And they used Ruby, and they had all these fail whales because the Ruby garbage collector wasn't very good and so on. So the VC investors forced them to say, well, you have to drop Ruby. This can't go on. You have to go on the JVM. And they said, we don't really like Java, but we prefer OCaml, but there's the Scala language, which is close to OCaml. So let's give it a try, even if it was widely experimental. And then a year later or so, some grad students at Berkeley picked it for their latest project, which became Spark, which now is a big, of course, a big open source project, big company behind it. So this was sort of, I guess, rather luck, fortuitous, you could say, but it sort of was in the right place at the right time, where you say these functional programming ideas, they gain currency, and the industry by and large is not there yet. Java didn't do it, C# didn't do it, none of the big languages did it. Now they all do, they all followed Scala in that, and they copied Scala in many ways to essentially add functional things to their languages. So all this went fairly fast. So one problem we had is that since we are academics and we want to have essentially precise foundations of what we do, we want to have a basis on which we can reason. The language sort of grew very fast, and it grew beyond what sort of our kernel was. So we, in the next decade, we sort of took the time to say, well, what is it really, this combination of function and object-oriented programming? So that led to a series of papers on the type systematic foundations, which is called the dot calculus, the dependent object type calculus. And based on that, again, we said, well, now with the language that has grown and essentially being pushed into niches, can we do sort of a redesign which essentially solves some of the shortcomings that we have identified in the meantime, and that improves on the strong sides of Scala that we have also identified. And that became Scala 3, which we released in 2020. And the Scala Center, which is Darja's part, then started around here. So it started fairly late in the process. I think that's important to remember. So why was Scala originally created? That was essentially a research thesis that I wanted to prove. The research thesis was that combinations of functional and object-oriented programming could be practical. And at the time, that wasn't at all accepted knowledge, because object-oriented programming was mostly in industry, so Java, C++, Ruby. And when it was in academics, it was untyped. It was languages like Smalltalk or Self, which all were explicitly dynamically typed, and which all made it sort of a point to say, well, we don't really want static types, because static types, that's Java, that's essentially constraining, that's bureaucratic. We want none of that. So the object-oriented thing was essentially, when it was dynamic, it was dynamically typed, and the strong functional languages, they were all in academics. Haskell, OCaml, which are both strongly typed, and Lisp, which is weakly typed, were all for academics only. So functional programming then is, what is it? So functional programming focuses on transformations of immutable data instead of word-by-word mutations. In a normal language, imperative language, I should say, which are sort of by and large the majority, your memory is made up of words, and these words are represented as variables in your language, and you can change them. So you have assignments to these variables, you have loops that test the current conditions of variables, and so on. And the functional programming has none of that. It says, well, all your data are immutable values, and you can transform them. So why is that good? Well, it's actually very close to mathematics, because mathematics is only about immutable values. If you say you have a polynomial, then the polynomial is what it is. You can't just change the coefficient and pretend you have the same polynomial. That just doesn't make sense in mathematics. So it's close to the theories. It keeps complexity in check, quite importantly, because it avoids side channels. Because once you combine functional programming with strong types, it means that everything, or a large part of your public interface, is actually laid down in the types. The function takes these parameters, and they have checked types, and it gives you a result, and that also has a checked type. Whereas if it would have a side channel that you say it also changes this global variable over here, that's much harder to control also in your head what it does. Much less compositional as well. And the other thing why functional programming sort of got a lot more mainstream over the last 20 years is that it solves some fundamental problems in concurrency, parallelism, and distributed systems, in particular because essentially caches can be invalidated without problem. Since there's only one value, you can cache it as often and anywhere you like, and you can throw away your caches and your computation doesn't change. None of that would work with immutable state. So Scala then is a unifier. It's both object-oriented and functional, and it's also, in a sense, a unifier in the sense that you can use it for both very small things, so single-line REPL. A lot of people use Scala like that, or there's a website called Scasty where you can just type in your 3-line Scala program and it will give you the result. And on the other hand, it's used for very, very large systems indeed. So there are at least 2 code bases out there that are over 10 million lines of code, all written in Scala. So that's really quite massive, the scale. And the important thing is that we can do this with essentially the same constructs down here and up here. It's basically all functions and objects. There's nothing else that we have to throw in. So in that sense, Scala, the name comes from scalable language. Yeah. Okay. So objects then are essentially our modules. I'm going to skip that quickly because they are sort of the standard thing. So challenges of this object and functional thing is initially it actually was quite difficult because the 2 worlds were essentially so far apart. So that's how many functional people see object-oriented programming. That's Office Space, this film with the What's Happening, the evil manager. That's what functional people saw object-oriented programming would be like. And that's what many object-oriented people saw functional people. So essentially all these crazy academics, they can't be trusted. Okay, so what Scala's, in a sense, approach was that we had functional objects where we say we will essentially trim down a lot what we do with objects. So originally, the definition of object by Grady Booch was that objects are characterized by state, identity, and behavior. And now we have eliminated the mutable state. We use structural equality. So essentially, we don't have identity. Two polynomials are the same if they have the same coefficients, not if they point to the same address in memory. And we concentrate only on the functionality. So what people do with it? So one of the large code bases is from a bank, and there are many other banks. So I just give you one example. The use cases are mostly in risk modeling. So what these investment banks have is they have a very elaborate systems that model the world. And modeling the world means that essentially every event that happens anywhere in the world that is of some significant financially are fed into these models as it happens. Within 15 minutes, they are fed in and computed. What you then have is lots and lots of Monte Carlo real-world simulations that say, essentially, how could this event essentially influence the world as we see it? And what comes out of these things in the end, and that's why they're important, is recommendations on the traders' desks that says, well, this option here would go a tiny percentage up in the recommended price or a tiny percentage down. And of course, if you do that better than the competition, you have a trading advantage. And that's why all these companies are very much after systems like that. So these systems are ideal for a Scala approach because the world is a typical object-oriented thing. It's modeled by a very, very large object graph indeed. And these simulations are all massively parallel, and that's why they need to be functional. So you never change these things. You only run things on top of the object graph. So in a sense, this is the Morgan Stanley solution is a I would say coarse-grained data flow solution that they over an object graph that they apply here. So that's what they do. Other adoption things are, of course, Twitter, who employed a lot of Scala programmers. Now it's a bit less, I guess. Coursera, the Coursera site, which has all our MOOCs, is also written itself in Scala. Duolingo, like if you want to learn a language, Duolingo, the site is written in Scala. If you're more for entertainment, so Netflix, the recommender systems are written in Scala. Disney streaming is essentially one of the showcases for essentially very high performance streaming I/O, written in Scala in Cat's Effect. Or Spotify has a lot of components as well written in Scala. So all these essentially internet streaming companies, they use Scala heavily because Scala turns out to be actually very good at this essentially very high frequency event processing model. Then there's Spark, which is essentially the fundamental, the leading software for big data written in Scala and has a Scala API in which you can query it. So in aggregate, we estimate that we have around 1 million developers with at least some exposure to Scala. And a harder number is how many registrations we got on the Coursera site, where the answer is about 800,000. So 800,000, or a bit over 800,000 subscriptions to our courses on the Coursera site. That gives you a good idea how many people got involved in that. Okay, so that's where we are now. Then let me talk a little bit about what we want to do in the next steps, and then let me talk a bit about challenges between essentially the open source model and the traditional academic model. So the new frontiers would be for us are to use capabilities for resources and effects. And in fact, resources and effects are two areas where we see a big difference between academic science and actual adoption. There have been hundreds of papers on these things over the last 30 years, but we see very, very little adoption of these ideas. And that's quite typical for a lot of what happens in programming language research. So the core insights of our research are that we can express both of these things as capabilities, and that we need a system to track retained capabilities in types, and we have developed such a system. So that idea will be fleshed out in an advanced grant project from the Fonds National, which will run over the next 5 years with about 7 people over 5 years. So it's a big project. It's comparable, it's equivalent in size to the ERC advanced projects of the European Union, in which Switzerland unfortunately cannot compete anymore. So I just give you a rough overview of what that is. Let's first define what resources and effects are. So for resources for us are values that come only with certain restrictions, such as a value that exists only a limited time. Afterwards, you can't access it anymore. Or you cannot access it from several threads concurrently, so that then we have a sharing restriction. Or if there can only be one copy of this value, then we have a quantity restriction. So examples are mutable variables, regions of memories, file handles, channels, database and network connections. Many things in computing are resources in that sense. So what's an effect? An effect for us is any aspect of the computation beyond the shapes of inputs and outputs that we want to track in types. So you could say anything that's not purely functional. So things that we also want to track, and those could be updating variables, for exceptions, doing I/O, or suspending a computation. Pure functional programming doesn't do that. So pure functional programming is up here, where we have no resources and no effects. Every value can be used as often and as long as you like. And everything is a pure function, no side effects. But of course, actual computers are not like that. Actual computers need to have, in the end, effects. And what's more, when they work through nothing but an effect. The most primitive operation on a computer is an update of a word somewhere in the store, which is an effect. So we simulate this thing in computers, but sometimes for efficiency, we need to fall back to the lower level. And in the end, we always need to fall back, because in the end, you run a computer to have an effect. So programming languages follow this model quite a bit. So there are high-level languages which are closer to lambda calculus. The most idiomatic language for that is probably Haskell, and then Scala is quite up there as well, and there are other functional languages such as Lisp or OCaml, which are all up there. Then we have low-level languages where essentially everything is an effect, and everything is a resource. That's C, C++. So for instance, everything is a resource in C, C++ because you allocate memory, and then you free memory, and after you free memory, you can't access it anymore, which is a source of many errors, of course, in C, C++, which comes from this resource typing. And then you have the languages in between, like Go, Java, and Swift, and many more. So that's one axis between computers and abstractions. The other axis is, to what degree do we do compile time tracking of these things? And the answer so far was not very much. None of these languages does a lot of compile time tracking. Some languages do a little bit, like Java tracks exceptions. That's one form of effect, but it only does that, and it's not very popular. Generally, people think that was a mistake that they did that. So it's actually quite difficult. One language that goes a lot further in certain dimensions is Rust. So that's a recent language that also was developed with an open source community process, just like Scala. And that does very fine-grained tracking of memory effects. So essentially reads and writes of variables. Rust is in its, even it has many modern features which also have functional languages have. It's by its nature, it's an imperative language. It's an effect-based language. It doesn't have a garbage collector, which means that many functional programming patterns are not available for us. So they can sometimes be simulated, but they're not directly available. There's of course a question: what if we also want to have fine compile time tracking of effects, but in a higher level language? So where this question mark is, and that's again not for lack of attempts here. So we had a lot of them. Linear Haskell actually made it into the language. Singularity, Mezzo, alias types, algebraic effects, many others more. Singularity was a project at Microsoft that actually Jim Laros, our former dean, was involved. He was heading that project. So The problem is none of these, as I said, really has any sort of traction in actual languages. And that's what we try to change with this Caprese project, which stands for Capabilities for Resources and Effects. So Rust got a substantial investment, of course, from many, first Mozilla funded it for a long time. And now there are many others, Amazon, Microsoft. It also got ERC funding. For Caprese, we have this large Fonds National project as a kickoff. And well, who knows, maybe that will actually get it into orbit where people are starting to use it. Good, so that's essentially what we want to do the next 5 years. There are challenges for this combination of doing programming language work, open source work, and research work in universities. The one problem here is that the traditional separation between science and developments has completely broken down. Essentially, developing new things is done in the open. Science is in a sense development. There's no phase where you do your science first and then you throw it over the fence and you say somebody else will develop it. That just doesn't work that way. I noticed that a lot of industrial science and computer science also is now this model where there's no real difference between science and development anymore. Before there was for instance, the Thomas Watson Research Center, or Microsoft Research Center, that essentially, or Bell Labs, where essentially you did the pure science and then you threw it over the product divisions. Now with open source, there are no product divisions that would pick your work up. So essentially everything is done immediately together. The other thing is, because it's all done in the open, community becomes very important, and in a good sense and in a bad sense. So essentially, it can be a big help. It can be an enormous boost and a multiplier of productivity, but it can also lead to lots of distractions with social strifes and bitterness and things like that. So it can lead to lots of drama, which is a big problem with that and has to be managed somehow. And finally, there's this tension between open source work and the traditional academic publication process. So the traditional academic publication process, as we know it, of course, relies on peer review, and peer review is important to get your papers into top journals and conferences, and that is important to get a job in academics. So basically, that's the thing. You do peer review as essentially a filter and a ranking of people for jobs, further jobs in academics. The problem is these peer-reviewed papers typically discount demonstrations of what does or does not work in practice. A paper like that is very, very hard to publish, as many of you probably have already found. So, for instance, I remember there was a paper close to my own work, but not from me, by Benjamin Pierce and David Turner on local type inference, it was called. And it was a very speculative paper, but it had some ideas. It got accepted. That was fine. And then they did a paper afterwards where they said, okay, so now we actually tried this idea on larger code bases, and it works to that degree. So that's how many type annotations we had to add that just gave you the data and things like that. That was a very important paper for the first one, of course, to see, well, here's an idea, does it work or not? Second paper never got published anywhere. So that's just not the kind of things you can do. The other problem with peer review is that it encourages secrecy and delayed publications. So essentially, before you have your paper stamped, you should keep it secret, because otherwise somebody might scoop you. Somebody might publish faster than you. So nobody essentially says anything until the paper is accepted. And that could take quite a while. I mean, might go through multiple reviews, could take years until it is accepted. And during that time, basically, you keep the thing secret, which is completely antithetical to open source. You could never do that. And the other thing is it encourages compartmentalization in both teams and time, I would say. In teams, it's your author team, and between them, there's full information flow. And then there's everybody else where you keep secret because you don't want to be scooped, basically. So essentially, you have these tiny islands of authors who sort of know about this work and you communicate, but everybody else is excluded. And the same is in time. Typically, a project runs as long as a grant runs. So there's a beginning and there's an end. And when there's an end, essentially, hopefully you have published things and you don't really care anymore. So it's somebody else's job. If this leads to, let's say, infrastructure or things people use, it's somebody else's job to pick that up. Only often that's actually not done. So it's not picked up and it falls into essentially an unmaintained state. Open source, on the other hand, says, well, if it doesn't work in practice, it's completely useless. That's the first question they will ask. Does it work in practice? If it doesn't work in practice, forget it. Time is of the essence. We want to know this immediately, and we need to inform everybody immediately, because if you want to get collaborator and people who actually help you and try these things out and maintain them maybe after you maybe hopefully essentially gave away the authorship of these things, they need to be involved from the beginning. So you need to be open from the beginning. And they want to be involved early on, and they demand also a long-term involvement. A project that dies after 3 years is useless for open source because, well, you can't have that. So what that leads to is that open source work is usually detrimental for publications. And I actually got these responses directly from PhD students where I said, well, this is very interesting what you do. You want to open source this so other people can do it. They said, no, I don't want users. I want to write my next paper. And that, I have to say, is the optimal strategy. If you want to do papers, that's actually a good strategy to do. Whereas open source communities, for these reasons, often mistrust science-oriented contributions. A criticism which I think is unfair and unfounded is often, well, essentially Scala, it's an academic language, it exists just so that people can write papers. So that's, for people who don't know this or who want to intentionally say something bad about Scala, that's an often used argument. Not for people in the know, of course, but it is an often used argument. So overall, I think I read a interesting blog post recently that I want to relay, is that science, the blog post said science is a strong link problem. That's actually the title of the blog post. You might Google for it, or GPR, or ChatGPT for it, for the summary. So what that means is that you typically have, in any project, you have some of the strong outliers, and you have some of the weak ones. And the question is, do you want to select for the good and accept that some of the weak ones will get in? Or do you want to optimize to eliminate the weakest cases and accept that you will not identify some of the strong ones? So an example for a strong link project is science, because in science, actually, in the end, these things matter. That's what brings the field forward. All these things are sort of the slow things which hopefully will essentially lead to some of those. And those will fall by the wayside anyway. Venture capital is a strong project. Venture capitalists say, well, we can have 9 failures for 1 win, and then we're still profitable. Sports is a strong project where you say you don't really care that some people are obese, as long as you have Olympic athletes, that's fine. You select for those. On the other hand, food safety is a weak link project. So you want to make sure that all foods are safe. It doesn't matter that at the time you maybe also drop off some food that claims to be a superfood. If it has bad ingredients, you still say, no, you can't have that. So food is a weak link project, or social security is a weak link project. You don't care so much that you have some millionaires here. You want to make sure that everybody has at least the minimum here. So there are different kinds of problems. And the important thing is that I think science is a strong link project. And open source fosters strong links, because open source essentially makes everything to maximize productivity and involvement of people. Whereas peer review tends to focus on weak links. Peer review is essentially to eliminate things that don't meet the bar, that are essentially not good enough for a certain conference. And I think that's a tension that we will have to solve in the coming years, or not, but it would be good to solve them. and it might lead to changes in the publication process. So there's some interesting ideas of what we could do maybe with different publication processes, but I'm out of time, so I leave you there. Okay. Thank you.
I think we are set. Okay. Wow, there are too many of you. Hi. So I'm Darja Ivanovic. Thank you very much, Noemi and Gilles, for first doing and pushing for this initiative, and specifically also for inviting us to open. It's quite a privilege. And on the other hand, it's actually a big honor to me to share the stage with Martin and Darja himself. This is the first time, and I'm quite nervous about it, because really following after he gives such beautiful talks is a bit intimidating. So bear with me. I would like to go forward with the talk, and I will speak about Scala and the story of Scala, but I'm mostly going to insert a little bit of the center, if I can actually, if this is going to actually work. Yes, so I'm going to insert a little bit about the center itself. And to do so, I will, of course, go back to the timeline that Martin already a bit spoke about, but I would like to focus on it so that I can answer the question, why the Scala Center in the first place? So Martin mentioned that already in 2001, the first Scala design has been made, but only in 2016, the Scala Center came to be. So there is like 15 years in the meantime that things were happening. And why in 15 years there was a need for a not-for-profit center is the question here. Another thing you could see from Martin's talk is that things were happening a bit spontaneously, and as the need would arrive, something would appear. So it's like, I don't know if you know Indiana Jones, you know, when he steps and then the stone appears. That's how Scala seems to be working all these years. So he mentioned that Twitter fell in love with Scala and picked it up. And that was, I'm going to quote Martin, that's when Scala was eaten by success. And the industry started picking it up. And when industry starts picking something up, they want fast and stable and not so much experimental and let's pray for Easter week to bring something. So Martin then, for that need and for that reason, with other co-founded, I think it's you founded and co-founded, there were other co-founders. Okay. Here at EPFL, at the Innovation Park, a company that used to be called Scala Solutions, that turned into TypeSafe, which is not very visible here, and eventually today is known as Lightband. So Lightband was the company that was powering Scala stable releases in the era of Scala 2. However, that then brought this need of more actual engineers getting those jobs. So people needed to be trained and to learn this new language. And again, Martin and his lab said, okay, if we need to teach people, let's continue with our open, in the open spirit, let's continue with that. And they created the MOOCs, the massive online open courses and published it on Coursera that are free and accessible to anyone that has internet and can get to do Coursera. In the meantime, they're also on edX and Extension School and so on and so forth. So basically, Martin opened what he's doing here at EPFL to the whole world. Martin was still busy while co-founding and founding and teaching. And in 2012, he started a fully new project, a research project, that at that time was called DOTI, and today it's called, again, Scala. So what we are seeing here is that there was this interest group, let's put it this way, that is more or less research-oriented, and yeah, this excitement of pushing the boundaries forward. Then there was this industry interest group that appeared. And with all these massive open courses, community started, well, there is a community already at the beginning, but then the community started growing and contributing back to the project. So we see here more or less three pieces of the puzzle that surround Scala. And then that's why, this is the reason why Scala Center exists, is to coordinate all these interest groups as a not-for-profit neutral entity, which next slide, I'm going to speak more about that. And then, of course, as I said, there was like more research that eventually merged back into the actual Scala. And I believe that Scala Center made a big contribution exactly for that particular release, which I'm going to focus on in a bit. So what is it then that Scala Center really does? Like, what is our role in this whole mess that Scala, I mean, a beautiful mess that grew out of Scala. So it's absolutely our mission to look at the Scala project holistically. Having all surrounding parts being treated as equal class citizens, knowing that that's the only way to ensure actual Scala's full potential. So as I said, we are a not-for-profit coordinating governance body that complements the stakeholder ecosystem in the Scala landscape. So what we do, the activities, as you can see, is developing and maintaining different courses and documentation, websites, and so on and so forth. So everything that has to do with education. We are developing and maintaining language itself to a certain extent, but more so the tooling around it, some libraries, and we go as far as creating... Yes. Somebody has a mic on. Yes, please. Thank you. So we also have like Scala JS and Scala Native. So Scala is now, I mean, multi-platform. So that's also what Scala Center does. We ensure that stakeholders are involved, for example, through our advisory board program, but there's much more to it. And finally, last but not least, we focus on building a welcoming and inclusive community. And today, I'd like to bring your focus exactly to that piece of the puzzle. Martin, luckily, already prepared the ground for this part. But I would like to show you with an example, like how does it really look to work with the community? What are the benefits? And what is it that Scala Center had to do to make sure that this community can actually contribute, but also communicate? So to do that, I will focus on what I said earlier, which is this release of the Scala 3. And so that's like the last decade. So I'm not going to go all the way back in 2001, but I think this is a good example. And especially I think it's good because today, literally to this day, it's 2 years that we released Scala 3. So we are celebrating, and I thought it was convenient also to share that success story. Now, as any success story, this one is also infused and embedded in a lot of failures and trials and errors. However, for the showcase, I'm going to make sure that we show the successful side. And then after we can speak about all the learning points and after this talk as well. So let's look at what in numbers, what it meant to release Scala 3. So it was, as mentioned, about 8 years of work with more than 100 contributors, out of which there were, I would say, even more than 20 PhDs and postdocs and lab engineers, 28,000 commits, 7,000 pull requests, more than 4,000 closed issues. So it's, and I have to say it was quite well received by the community 2 years ago. And so what this shows is that it was in the end like a very massive theoretical and then technical undertaking. Now, I would like to take a moment to show you in a video, 3-minute video. It's like a visualization of what those 8 years look like, and especially from the community perspective. So let's try this and this. Enjoy. So I hope you enjoyed the little. Bravo, Martin. Bravo, everyone. So what I would like to, I mean, you've seen things and probably you have many questions about it, which we can wait for later. But there are three things I would like to highlight within what we just saw. So at the very beginning, we see about the first minute of a 3-minute video, which represents, I don't know, a year or something. Martin was working alone on it. There was like one idea, one person testing things out. And after the initial contribution of from the EPFL students, which we know because we see some of the names that we recognize at the very beginning, it soon becomes, it goes out of EPFL. This is what Martin was speaking about. Like you want to test, you want to see, you want to also like get others excited about it because it's just so awesome, I guess. And you see that the community is taking more and more projects, and they're like helping, experimenting, playing around. I mean, it's going in all kinds of directions. But most of all, what you can really see very well captured in this video is the actual power and the beauty of open collaborative work. Like this is literally what it represents. So data visualization was done by our dear colleague Anatoly. who is here with us, who might need to answer some questions about how it was made and how other people can make it. But the thing is that he based this visualization on data from the GitHub.io repo. And so what you really see here are only the things that got merged and committed and finally released. So actually, the more interesting thing is all the things you don't see here, that are all the things that were tried but not ended inside. And also, again, you see the technical work that like purely technical commits to the project. And then there is the second part that is also not represented here, but is a topic for me today, which is what did it actually take? What my dear colleagues would say overhead, and I call it my work. What is it that what did it take to actually make all these technical commits possible within the open source community? So I'm going to click and hope that the next slide will show. Yes, perfect. So all the things that are surrounding these impressive stats, what are those? And I'm going to name a few, okay? So in order for people to actually do the work, they need to communicate in many, many, many ways. A lot of people communicating all the times through many different channels. So it's Scala Center, well, we took it upon ourselves to provide the infrastructure for this communication that can then actually help us in getting the feedback and then making certain action. I mean, when I say us, I mean literally everybody that was working on the Scala project, and not me. So this is just one example of a forum that we are hosting and moderating. Then somebody needs to lead the decision-making processes, such as Scala improvement process, which was a challenging thing during the Scala 3 release because there were too many changes, but this is how a Scala improvement process can look, because anybody can actually propose a change or a feature to the Scala project. More communication at the time. I think there was also Gitter, maybe even Skype. I mean, it was so long ago, but I put here as an example just Slack. I think Discord was not yet in the game at the time. Then the communication itself on the project itself, so on issues and PRs and so on and so forth. Then from time to time, we needed to make sure that what is being done is actually applicable on a broader user cases. So we would do certain surveys. And then we would need to broadcast certain information through our communication channels. Now, there are also all these things that have to do with the technical side that are not necessarily directly working or contributing to the Scala project, such as how are we going to migrate? So everybody, like that was the buzzword of 2018, like, oh, Scala 2 to Scala 3 is going to be the same as Python 2 to Python 3. And we're like, no, we are going to do a better job. And we did. Okay, that required a lot of migration tools, migration documentation, general documentation update, update of all our MOOCs, Martin's teaching here. Of course, the Scala book deserved a 5th edition. And one thing that I didn't put here, but I need to say it out loud, of course, there was a master spreadsheet somewhere there actually coordinating all these things. I don't know why in 21st century spreadsheets are still like the thing that we default to, but it works. So yeah, so that we did with Anatoly, and it was a glorious one. Things that I can still mention is that there are all this other work that goes in like tooling ecosystem, libraries, community of supporters, and much, much more. So these are the things that surround the video that you saw, on top of the things that you didn't see in the video. And to wrap it up in a number, because I know analytical people like numbers, again, Anatoly came to rescue me yesterday. I tried putting like a dollar sign on how much did this cost over 8 years. And we only took into account LAMP, so Martin's lab, people's salaries throughout the years, Scala Center, Lightband, and Virtuous Lab. That's a company that is currently backing Scala 3. So only the companies. We did not take into account people that were doing it in their free time, or on their company time, and so on and so forth. So the number that we came with is, in 8 years, it was like 18 million francs that were spent on what we can actually calculate yesterday. Okay, so I would say it's even, I would not dare saying it's double that, but it's quite a lot more than that. So I wanted to make a pun. It turns out that free software is not that cheap after all. Ha ha ha. Okay, so why am I saying, like, what is my point here? So there are 3 points I would like to make based on everything I showed here, that I would really like you to retain, especially if you are like just starting your project, you know, or you're somewhere on the line of becoming successful in the community, like getting more traction. So the first thing that I want to highlight here, that I mentioned a little bit earlier, is that you know, Rome wasn't built in a day, so neither was Scala. So all this success with Spark, and well, we were going to stop saying Twitter because we need something new, but yeah, Disney Plus and so on and so forth, it didn't come really overnight. I mean, there's like 20 plus years, and Martin had to like do things over and over again on his own, and then gather people and push many boundaries. So it takes dedication, takes time to develop a successful project. The second thing is that what attracts community in the first place is definitively the project itself, your technical thing, like the video that we saw. That's what attracts the community. But what really keeps the community running is the engagement and the opportunities to contribute and to bond with people that share similar passions. So I also tried to being funny here. So the technical solution, let's call it this way, is the beating heart, but really the community is the soul, is the one that really pushes it forward. And we felt it on our skin all these years. And finally, benefits of working with the community are really endless. And I'm not going to list them all here. And Martin already actually did a good job at showcasing that. But he also mentioned that if it's not done well, the community engagement, it can be overwhelming, and you know, it takes only one bad actor with a lot of passion and time to bring you down, to get this toxicity around. So if there is one advice I would put out there, is that community contributions are priceless, but make sure that the infrastructure is in place to honor it, and anticipate and design for the community engagement. Even if you're now one person, you probably have 1 or 2 colleagues. That's already going towards a community. And as you saw on the video, Martin is 1, and then there were like 2, and then 5, and eventually it became a community. Okay, and so finally, that said, if we did have, could go back in time, and where is my... Okay, if we could go back in time, or I had the magic wand, I wish that we would create the Scala Center closer to the moment community really started picking up, than where we are, like almost at the very end. Because I believe it could have been also even more stronger, let's say, this way. Maybe not. In any case, that's my dream. So that said, I'm coming to the end of my presentation. We are here at EPFL, next door to you, with over 20 years of experience, from like language design to like crisis in community management, to communicating, to infrastructure building, community building, and so on and so forth. So wherever you are, in the spirit of openness, please feel free to come. We are very happy to share more failures, lessons, successes, and other. We believe in deduplicating efforts, so please come and speak to us. Other than that, we always have these like micro events, so you can just hang out with us for Scala lunches or Rockets workshop, and there are other things. So please reach out. I put up a photo of our team, and you're going to see many people in orange t-shirts. Thank you very much for coming in orange t-shirts today. So this is a team that was there to release Scala 3. In the meantime, some of the people left and some of the people came back. But for sure, if you see us in this t-shirt or in orange t-shirt, that means we are ready to answer your questions. And you can always approach us, and we are very, very happy to speak. Well, at least I am very happy to speak about myself. So thank you very much. And I guess it's the question round. Okay.